Today's topic is dilation of figures about the origin, and you can use April 28th. We have 5 pages to our note packet, so this is what the first 3 pages look like. And then the last 2 pages. Hopefully most of these are back to back. So let's start with the definition of a dilation. Basically, this transformation will either enlarge, stretch, or it will shrink your figure. It's also making the enlargement or the reduction around a fixed point called the center of dilation. In the picture, we can see that the green rectangle was my original figure, and the red figure is my image because of the prime notation. The center of dilation happens to be right here in the center at the origin, and basically all the points were pushed out or stretched away from that center. When you dilate, you should be able to see your pre-image and your image on the coordinate grid. If you look at the example here on the right, what you can see are lines connecting the pre-image and the image points. And when they all come together, they intersect at the center of dilation. So in this picture, the center of dilation is not really in the center of either figure. It's off to the side. So we can see they're listing the center is at the origin. Now the scale factor K equals 2, we're going to talk about in a second, but that confirms to me that the red triangle was my pre-image and the blue triangle is my image. So the point 1, 1, if we connect it to its corresponding part, it's now at 2, 2. So it just pushed it twice as far away from the origin. Anytime that you perform a dilation, your figure will be enlarged or reduced by a scale factor, constant of proportionality, or K. We saw this in our ratio and similarity unit. When we abbreviate a dilation, we use a capital D, and then in subscript, you put the scale factor. So this is a dilation of 2. This will make the point or image twice as large. We can also dilate by a scale factor of a fraction or 1/2, and that will shrink my figure. So to start with some basic rules, if my scale factor K is less than 1, I should automatically be able to tell that the figure is reduced, even before I start the process. If K is greater than 1, then I know that the figure is being enlarged. So you can see here the pre-image of the penguin. This one is definitely a reduction, so the scale factor is less than 1. In the map of the United States, the pre-image is here on the left. It did get larger, so I know that the scale factor K is greater than 1. It's also possible for the scale factor K to be negative. So we're still going to enlarge or reduce the figure, but the fact that the scale factor K is negative will actually change its direction. So the orientation will change. In my picture, the blue figure is my pre-image. If you dilate it by a scale factor of +3, it will enlarge and become the green figure. But if you enlarge it by a scale factor of -3, it's still 3 times as big, but now it's here in pink and it's been flipped over. It's also possible that the scale factor could be 1. If the scale factor is 1, the pre-image and the image will be congruent. So let's see if we can figure out the rule. The pink triangle is my original figure. The blue triangle is my image. So for A, we went from -2, -2 to -4, -4, and it did get bigger. B went from 1, -1 to B prime 2, -2. So it appears as though we're multiplying by a scale factor of 2. If you are dilating about the origin, our general rule says you can take any point P located in the coordinate plane at x, y. It will map itself to P prime. you're going to simply multiply the scale factor k by the x-coordinate and the scale factor k by the y-coordinate. And again, this has to be center at the origin. In our first example, it says, what is the image of the point 5.3 under a dilation of 8? This is our scale factor k, and you're going to multiply 8 times 5, which is 40, and 8 times 3, which is 24. So this is the new location of our point 5.3. Number 2, under a dilation where the center of dilation is the origin. You don't have to do anything different. That just confirms that this multiplication rule is appropriate. The image of A at -2, -3 is A prime, -6, -9. What are the coordinates of B prime, the image of B at 4, 0 under the same dilation? So we first have to figure out the dilation rule. We went from -2 to -6 and -3 to -9. It appears as though I'm multiplying by 3. So I'm going to say that the dilation rule is 3. If I use that same dilation rule on 4, 0, we'll be able to locate B prime at 12, 0. For number 3, in which quadrant would the image of point 5, -3 fall after a dilation using a scale factor of -3? Well, let's first dilate the point and see where it's located. So if I multiply both the x and the y by -3, my location will be at -15 and +9. If you can visualize the 4 quadrants, I would be first traveling left and then up, and that will be quadrant 2. In example 4, it says, under a dilation with respect to the origin, the image of P is P prime. What is the constant of dilation? They're looking for the scale factor. I went from -15 to -5 and from 6 to 2. You can tell that you're dividing by 3, but remember, the dilation rule is a multiplication rule. So instead of saying divide by 3, we're going to say that we multiplied by 1/3. In example number 5, we're given 4 ordered pairs. We need to dilate quadrilateral ABCD by a scale factor of 1/2 to create the prime image. I'm going to start by graphing ABCD. I did not label my points because it will be a mess. Make sure you label all of your vertices. We're going to apply the rule of dilating by 1/2. So we're going to multiply 4 by 1/2 and 0 by 1/2. So A prime is at 2, 0. I'm going to go through and multiply the B values by 1/2, the C values by 1/2, and D. Don't forget to put your rule above the arrow. And now that I know where the new locations are, I'm going to go ahead and plot my quadrilateral. That's the image. When I look at that, it's definitely the same shape. It is facing the same direction, but it's clearly not the same size. For example number 6, we have 3 points given to us. I'm going to go ahead and plot those 3 points and create my triangle. We're now dilating by a scale factor of -2. So triangle XYZ should get larger, should be double the size. So I'm going to multiply all these values by -2. So X prime will be located at 4, -2. There's Y prime and Z prime. And I see that mistake right there. Now that I know where they're located, I'm going to go ahead and plot that figure. And my new triangle does look to be twice as large, but you can see that it's been flipped over. That's the negative aspect of the scale factor. So it did enlarge it, but it made it face the opposite direction. For example, number 7, we have another triangle located at MAP. We're dilating by a scale factor of 2/3. I automatically know that my image should be smaller than the original. The use of the grid is optional. So I'm not going to use the grid. I'm going to go through and multiply -6 by 2/3 and 3 by 2/3. If you need the iPad to help you, you can do that. Typically, when you're multiplying by a scale factor that's fractional, the points tend to work out really well so that you won't be in between blocks. So for M prime, A prime, and P prime. And there's my dilation rule right above the mapping. Let's first talk about our invariant properties, things that didn't change when we dilate a figure. First of all, the angle measure is preserved. We know when we studied similarity that you can enlarge or reduce your figure, but corresponding angles will always be congruent. Any sides that were parallel on your original figure will continue to be parallel on your image, so parallelism is preserved. Any points that were collinear on the pre-image will continue to be collinear on the image. Now, we also have variant properties, things that did change when we dilated the figure. First of all, the size was not the same, so the constant of dilation, or the scale factor K, will keep the pre-image and the image in proportion. Remember, we can go around from the left side of each figure to the top side to the right side. All the ratios of the side should be the same. So that confirms that distance is not preserved. If your pre-image had side lengths of 4, your image might now have side lengths of 2. And the orientation may change. If your scale factor is negative, we're going to flip the object over when we dilate it. So, under a dilation, a figure and its image are similar. They're not congruent. So dilations are not isometries. An isometry was a rigid motion. Well, this wasn't rigid. We shrunk it or we enlarged it, so we were kind of pulling at it. It didn't stay constant. Depending on the type of scale factor, your dilation could be a direct transformation if K is positive, and it will be a non-direct transformation when K is negative. So we've got a lot of variables happening with the dilation. Your homework assignment should have 3 pages. It'll start with dilations about the origin. The last problem here is number 24, and you'll see that it's got a lot of white space. Make sure you're doing full mappings when you complete these assignments. If you have any questions about any of the homework problems, please make sure that you get in contact with me. Otherwise, have a great day.